Graphing the quadratic equations from the vertex. Here's the general form of the vertex. Notice that this looks very similar to the lesson we did on completing the square. Whenever you had an expression and you were told to rewrite it by completing the square, many of them turned out to be in this form. Quantity squared of x minus h close the quantity plus k. That is the vertex form of a quadratic equation. Now here is a graph of y equals x squared. Look at where the vertex is at. What point is that laser on? It's 0, 0, and the general form looks like this though. But here's why we can still get a vertex out of that. X squared. Could I not write x squared as the quantity squared of x minus 0? If I take 0 away from x, does it change the value of x? No. So I can write it like that. And is there anything out here to the end of this yellow equation? Any numbers, any constants? Anything written after x squared? So if there's nothing after it, then what is the number that's there that's just not written? If there's no number there, it still has a value, it's just what? Starts with a z. 0. So we can rewrite that yellow equation just into that form by not changing the value at all. And this is why the vertex is 0, 0, because look at where 0, 0 is at in this equation. In this one, we still have nothing written out to the right. It's still a 0, but now we have x minus 1 in there. Remember, the general form is x minus h, square the quantity, and then plus k. But look at where the vertex is at. What is that point? Can you identify the point that that laser is on?
Or 0, 1.
Not 0, 1. It's 1, 0, right. Look at your equation up there. Can you see where I came up with a 1 and a 0? Alright, remember the general form has a minus sign in it. So that if you're looking for h, and h is the x value of the vertex and k is the y value of the vertex, you get it by doing 1, 0. That's why the vertex is at 1, 0. So on this graph, look at where what point is this at? 2, 0. So here's where the 2 came from, and that's where the 0 came from. That's the vertex. What about this one? What point is that? 3, 0. 3, 0, so here's where the 3 came from, and here's where the 0 came from. So I'm going to put all those graphs together on the next slide. We started here, and remember that one was x squared. And then the next one bumped it over to the right, and that one was x minus 1, quantity squared. And then we bumped it over again by making it a 2. And then it went over again by a 3. The thing to get from this is the following. If this is your general form, and it's got a minus sign in it to start with, you're only taking out the opposite of that. So if it's minus 1, think of that as negative 1, but switch it to be positive 1. That's why we end up there, here, and here. You may think by looking at the equation that it should be at negative 1, negative 2, negative 3, but it's not, because it has a minus sign in the general form. So you take out the opposite of that, and it moves it this way, like that. Let's start over and go back to the original graph. Here is y equals x squared. Remember, you can write that as x minus 0, square the quantity, and plus 0. But look what I'm doing now. I have a plus sign in there, just like he was talking about before. What point is this vertex on now? Negative 1, 0. So look at this. The negative 1 came from here, and the 0 came from there. The general form has a minus sign in it. Whatever is in here, or actually whatever is in here, you do the opposite of it. Because in order to get a plus sign there, at some point you have had to put in a negative 1. Double negative is plus. That's why that's plus. And this is why we are at negative 1 there. And if I had a plus 2 on the inside, my vertex ends up here at 0. Or actually it's a negative 2, 0. Negative 2, 0. And if I had a plus 3 with a strange mark that just showed up there, that would be a negative 3. Here are all those graphs together. We started back here with this one. That was y equals x squared. Then we put an x plus 1 in the parentheses and it bumped it to the left. And then it went to the left again for plus 2 and then the left again for plus 3. Alright, now we're going to put something other than 0 at the end of it. Here's what we're going to start with. We're going to start with y equals the quantity squared of x minus 1, which means there's a plus 0 at the end. That's why our vertex is 1, 0, and here is 1, 0 there. Now look what happens when I put a number at the end of this. What happened when I put a plus 1 at it? It moved it up 1. This is where we started, and it moved it up 1. So if I put a plus 2 at the end, here's where my vertex was to start with. It now moved it up 2 places. And I started here, and if I have a plus 3, it moved it up 3 places. This point here is over 1, up 3. There's my 1, there's the 3. That's the vertex of the graph. And here are all of them put together. This is where we started. That was plus 0. And then here we added 1, we added 2, added 3. So what is the vertex? It's h and k. That's what you have to get out of all of this. But remember that this is minus h, and that if you get a problem that ends up with a plus in it, such as if I had y equals the quantity squared of x plus h, close the quantity plus k, I would really be taking out negative. K does not change. It is what it appears to be, whether it be minus 3 or plus 1 or whatever. Yeah, it can be. Yeah, it's just you can't do much with it except plot it on a graph. It doesn't change anything else. All right. I'll give you the equation. You have to name the vertex. What is the vertex? Negative 4, 6, right. What is this one? 2, 3. What's this one? 4, negative 1, yeah. What's this one? Negative 5, negative 1. What's this one? Negative 6, 3. All right. Here's a special case. Y equals x squared plus k. Remember the very first graph that we did? It was y equals x squared. And we rewrote that so that we could make it look like this. Y equals quantity squared of x minus 0. And then whatever the outside value was. keep in mind that whenever you see y equals something x squared plus a constant, that the x value of the vertex is just going to be 0. And then this number out here will give you whatever it is for the y value of the vertex. What is the vertex in this one? 0, negative 2. What's this one? 0, 6. What's this one? 0, negative 5. 0, 7. All right, now we're going to go backwards. Instead of getting a vertex out of an equation, we're going to create the equation from the vertex. So here's the vertex, negative 2, 5. If I have a vertex of negative 2, 5, I need to remember that I've got to put it in this form here. So if my vertex has a negative 2 in the point, then it must go into the problem and create what? A plus. I need a different marker. There we go. So I would have y equals x plus 2. I left out the x. And then I would have positive 5 or minus 5? Plus 5, yeah. In this one, I would have y equals quantity squared of x and then what? Minus 6. Close the quantity and then minus 3. For some reason I've started to put a plus, but that is minus 3. What should this one be?
Y equals quantity x minus 4 was quantity squared.
Yeah, that's it. Y equals quantity squared of x minus 4, close the quantity, plus 2. This should be y equals the quantity squared of x plus 8, close the quantity, minus 10. We should have this, y equals the quantity squared of x minus 5, close the quantity, and then plus 3. Here's an application. Caitlin has 60 feet of material that can be used to make a fence. Using this material, she wants to create a rectangular pen for her dogs to play in. What dimensions will maximize the area? Okay, so let's assume that she has 60 feet of fence, and here's what we'll do. This is her 60 feet of fence, that line. And she's going to turn that into a pen, so she's got to shape it into a rectangle. I need a smaller marker. There we go. All right. Now she's going to turn it into a play pen, so this pen could be, we don't know yet, but it could be a square, it could be a rectangle, it could be something as crazy as this. So let's just talk through some of the possibilities that this could be. Remember, she has 60 feet of fencing to use. What if she did this? What if she had a 24-foot length there and there? How many feet of fencing would she have used so far if she had 24 on both sides? 48. And how much would be left? And half of 12 is 6, so she could do that. Now, that's 6 feet wide. That's not a whole lot of room for a dog to go in circles. He might just be able to prance back and forth 6 feet. He could run 24 feet, that's fine. What if she had a 1 foot wide, let's do it here, 1 foot wide. She's used 58 feet. So she would have 29 feet on either side left to go. Is that dog going to enjoy a 1 foot wide pen? No. So what if she came up with something like, I don't know, 10 feet for these sides. So she's used 20, and she has 40 left over, so that would be 20 on either side. I mean, the dog might enjoy that. But there's a way to figure out the precise maximum area that she can have without having to go through a guess and check on all this. And here is how you do it. It says, let W be the width of the rectangular pen in feet. Write an expression that represents the length when the width is just W feet. So let's make another box here. And our width will be this. Our length is this. And we know she has 60 feet of material to use. But the problem is asking us to make an expression that is in terms of L. L equals something. Let's start from the very top. She has 60 feet of fencing. How could I take away some stuff such that all I would have left would be these two lengths here? How can I get rid of my W's? What operation allows me to... We can minus W, yes. Now, if I minus W, I've taken away this one. How am I going to get rid of that other W? Not square it.
I'll put 2 W.
That's right. Or we can just take away another W and we can combine our like terms in another step. He's right. So we've taken away both of our W's. Now, do we have just one L left or do we have 2 L's? We have 2 L's. All right, when you have 2 of something, let's say I had 1 bottle of Mountain Dew and then I had another one beside it. I have done what to my original number of Mountain Dews? Doubled it. Yes, I've doubled it. So in order to undouble something, what operation do? You divide by what? 2. So there's an expression that leaves me with just 1 L. But like he said before, instead of taking away W and taking away W, what could we take away? 2W, yeah. So let's combine those terms. Is there something I can do to that expression to reduce it?
Take away the 2, negative 2. Like, reduce it.
Yeah, I can reduce it by dividing these 3 numbers by what? 2. Yes, I can divide them by 2. So if I do that, I'm left with L equals 60 divided by 2 is 30, and minus 2W divided by 2, W. What's 2 divided by 2? 1. Do we need a 1 on the bottom? No. So this is it. This is your expression that is equal to L. And that's what we were being asked to find in part A. But part B says we need a function, A of W, that describes the area, which is why it's called A, in terms of the width. So your function has got to start like this. A of W. That means I'm putting in a W, a width, and I'm getting back an area. How do I find the area of a rectangle? What's the formula? Length times width. Did we just find an expression that we could substitute in for L?
Yeah.
What was it?
L equals 30 minus W.
30 minus W. So put in 30 minus W for L. That's what we just put in for L. And W can just be itself, so multiplied by W. Now we can't just leave it like that. We have to come up with an equation. So how about I find a marker that's a little better than that? There we go. How about A of W equals this thing multiplied out? Like, what's W times 30? 30W. And we have our sign in the middle. What's W times W?
2W.
Not 2W. W squared. Right. Now think about all the quadratic equations that we've looked at over the last 2 weeks. They all started with what term first? Not the B term. The squared term. Whatever term is squared comes first. here is the general form of a quadratic equation. A x squared plus bx plus c equals 0. So the term that has the squared with it is usually first. So that's what we need to do to this right now. How about putting this minus w squared first and then plus 30w behind it, so it's easier to work with. Now, completing the square, this is what we did more than a couple of weeks ago, where we completed the square on something that had an item in this spot other than just a positive 1. Remember, we grouped these together, and if this item was something other than a positive 1, we did what with this item? Took it out. Okay, so A of W equals the negative 1, which we just write a negative sign. That's negative 1. And then we divided each of these items in here by that negative 1. What's negative w squared divided by negative 1? Positive w squared. And then what is 30w divided by negative 1? So we'll put minus 30w. And when we completed the square, we had to leave a space after that last term, which we can do here. We left a space there so that we could find half of the middle term. What's half of 30? Half of 30 is 15. What is 15 squared? 225, right. So I'm adding 225 here, but did I really add 225? What did I really do? I subtracted 225 because this negative 1 out here must be acted upon by this to create a negative 225. So if I've subtracted 225 and I'm going to stay on the same side outside of these parentheses, I must do the opposite of that to balance it out. So I must add 225. Now put it in the vertex form. So we have A of W equals the negative quantity squared of your variable, the sign from the middle, minus, half of 30 is 15, and then you still have your 225 outside. Does this form look familiar? It's the vertex form. And what is the vertex according to this equation? That's right. And remember that W, what you're putting into this function, which is the x value, is 15. That is the width. The 225 is the result. That's what you get out of it. That is the area. So at what width will she maximize the area of her dog pen? 15. So if I have a width of 15 here and there, what are the lengths of my figure? 15. They all add up to get 60. So the area would be 225. Remember one of those scratch things that we did where I wrote the triangles? One of them came out to be 200 square feet. So we got close to it by guessing, but you can get it exactly by doing this.